Hello, my friends. Due to unfortunate circumstances, I need to offer this week's course asynchronously online. I hope you will excuse me for this inconvenience. And I will start with a short video where I'm going to summarize the things that we have done about this module. So far, we were considering the optimal load sizing problem. So let's go over the basic assumptions of this problem just for remembering them. So we have a demand in the future that is known. The behavior of the demand is known, which means the demand is deterministic. So we are just going to solve an inventory planning problem under deterministic demand. However, the demand changes through the planning horizon. So we are just going to plan our inventory levels, or if this is a production problem, we are also going to plan the production over a finite planning horizon. So this is not a very long-term problem. So we have said that a typical aggregate planning problem fits to this framework, and the planning horizon is finite. Uh, Now, the demand through this planning horizon changes dynamically. What does that mean? We know how the demand will behave, but the demand can change either continuously or discretely over the planning horizon. So how do we approach this problem? The main idea is to discretize the planning horizon. So even if the planning horizon is through the planning horizon, the demand behaves continuously, it changes continuously. We basically discretize the planning horizon and we assume in each discrete period, there's a constant rate of demand. Okay. So this is how we are going to deal with this problem. After doing this, the problem gets simplified and but still we say that in these discrete periods from period to period, the demand amounts can change dynamically. And that problem is called the load sizing problem. We basically ask this question: in which period we are going to replenish our inventory, in which periods we are going to do this, and how many units we are going to order. Okay. If this problem is in the production context, in that case, we ask the same question: are we going to initiate a production run this period, and how many units we are going to manufacture in this period? Now, this problem can be optimally solved through integer programming approach or the dynamic programming approach. If we are talking about a certain product that has a measurable inventory, in that case, we can use mixed integer programming models, but at this point, we are just going to assume integer quantities for the order quantities or order levels or the inventory levels. So we have studied the problem from the in integer programming perspective. We have developed an integer programming model for that. And let's just skip to this model immediately. So we have an objective function here, which is the total inventory, and if we are in the production context, the total inventory and the production cost throughout the planning horizon. Now we have three types of cost components in it. If we initiate a production run or if we release an order in a certain period, we need to pay a fixed ordering cost or fixed setup cost associated to production initiation that is equal to Ki. Now, yi is a binary decision variable. If we are going to initiate production or if we are going to release an order, then yi must be equal to 1. And that is just going to create a contribution of this fixed ordering or fixed setup cost into the total cost. And then in the ith period, if we are going to manufacture or if we are going to order Qi units of inventory, in that case, for each unit, we pay CI dollars. This is the unit purchase cost or unit manufacturing cost, unit production cost. And finally, when we end a certain period with XI units of inventory, on-hand inventory. Then we need to carry this inventory to the next period, and the unit carrying cost of inventory from I to the I plus first period is denoted by HI. So we have three components: the fixed ordering or fixed setup cost associated to each period from 1 to n, the production cost, this is the variable costs changing with respect to the production quantity or the order quantity, and the third component is the inventory carrying cost from a period to the next period. So associated with this problem, we have several constraints, one of which is the capacity constraint. In any period, the production quantity or the order quantity can never exceed the capacity or the maximum ordering level, which is denoted by Qmax. I mean, this is an optional constraint, by the way. If your production capacity enables manufacturing any quantity, or if your supplier is okay with releasing any size of order, then you can simply ignore this constraint. The second constraint creates a dependence between the YI decision variable, which is related to initiating a production or releasing an order. So this is a binary variable. And if this binary variable is equal to 1, then you can manufacture or order any quantity, Qi. So this means what? If Yi is equal to 0, Qi must be equal to 0, which means you can never release an order or you can never initiate a production because you are not paying the fixed ordering or fixed setup cost. If Y is equal to 1, so if you acknowledge that you are going to pay this fixed ordering or fixed setup cost, then you can release an order or you can initiate a production. Qi can be positive, okay? So this constraint is basically creating this dependency between Yi and Qi decision variables. Now, if Yi is equal to 1, then big M value will vanish, and in order to satisfy this greater than or equal to 0 constraint, Qi must be 0. Okay, Qi can never be positive in that way. If Yi is equal to 1, however, then the value here multiplied with big M will be infinitely large, and subtracting any positive quantity will always keep this above 0 level. Therefore, you can manufacture or release an order of any size you want here. Or you can combine the first two sets of constraints by replacing big M value with Qmax here. And then you can delete the first set of constraints. So you can combine these two sets of constraints in a single set. The third constraint here is the balance constraint that basically relates the initial inventory level of the ith period with the ending inventory level of the ith period. So xi minus 1 is the ending inventory level of the previous period. Okay, I minus first period's ending inventory, which is also equal to the initial inventory of the ith period. And xi is the ending inventory of the ith period. So this relationship is explained by this equation in the direction of time. So we say that the ending inventory level of any period is equal to the beginning inventory level plus the order quantity, which is just going to be introduced to our inventory, and minus the demand. The demand will withdraw units from inventory, and that will be calculating our ending inventory level for this period. Okay, and by the way, we do not allow back ordering in the last week's context. So here, by introducing this equation as a constraint, what we must do is we need to, so let me do it again, let me show it again. All these decision variables, the order quantity and the ending inventory levels must be collected on the left-hand side of the equation. Obviously, in order to write an elegant mathematical model here. So it's not necessary. I mean, this equation here is explaining everything, but we usually write the decision variables to the left-hand side and the parameter, the resource on the right-hand side. Here, the resource parameter is basically the demand itself. And for each period, this balance equation must be satisfied. And obviously, we are deciding about the order quantities or whether we are going to initiate or release an order or not. But indirectly, we are also deciding about the ending inventory level. So they are decision variables as well. Finally, the yi decision variable is binary. Qi is integer and it must be non-negative. And xi, the ending inventory levels, are also integer and non-negative. Obviously, if we are considering a inventory an item that has a measurable amount rather than a countable quantity, in that case, qi and xi values are not supposed to, they are not necessarily integers. So the integrality constraint in that case is unnecessary. However, we are just going to assume the integrality constraint at this point because we are also going to solve this problem with the dynamic programming approach. The integrality assumption obviously going to make these things easier for us. So in the dynamic programming model. So we have to solve this model using a solver, or I mean, basically we are using the Microsoft Excel solver hidden for such a small size problem, obviously. And we have applied this in the last week. And we have solved a problem here, the question 1 here, and we have found its optimal production and inventory policy here with a minimum total production and inventory cost. Then we have explained that this problem can also be solved by the dynamic programming approach, namely the Wagner-Witten algorithm, developed in literature. This is a very famous algorithm. So the Wagner-Witten algorithm uses the forward recursive equation of the dynamic programming model. And we consider, when we are developing this dynamic programming model, we consider each period of the problem as a stage, and the order quantities or the production quantities as alternatives, and the ending inventory levels as states. Then we develop a recursive equation here. The recursive equation intends to calculate the minimum total amount of inventory cost in the end of the planning horizon, such that we end up with a certain inventory level xi. But in order to calculate that, it asks the minimum total inventory costs until the end of the previous period by such that ending with a certain inventory level calculated by the ending inventory of the ith period and the decision variables, decision alternatives in the ith period. So this is called the recursive formula because this function here calls itself in it, and it requires a calculation of the previous function. So if this is a, let's just say, n stage problem, then calculating gn requires calculating gn minus 1. Calculating gn minus 1 requires calculating gn minus 2, so on and so forth until g0. And g0 obviously developed, basically constitutes the initial condition of this problem. And g0 is 0 because at time 0, so far, you do not have any activity. You have not decided about anything yet. At this point, even if you start with a positive inventory level to this problem, you do not pay any cost for that because all costs are already paid as sunk costs. So the initial condition is G0, the initial inventory level. Given that you have an initial inventory level X0, the total amount of costs up to this point, which is again the current point, is equal to 0. So this recursive equation will force to calculate in every iteration from n to 1 the gi values, and finally the g0 function will be equal to 0 as the initial condition. That will help us to find the ultimate result. So we have solved the same problem using this recursive equation. So we have started at stage 3 because this was a 3-stage problem. In each stage, we had a different fixed ordering cost. We had a different unit purchase cost, and we had a different unit inventory carrying cost. And the demand was also changing dynamically, and there was a capacity of or limit on the order quantity in each period. The initial inventory level was 1, and we were trying to calculate the minimum total inventory and production costs in the end of the third stage or third period, such that we end up with zero level inventory. So we have used this recursive equation, which I'm not going to explain further because in the following videos I will explain it by introducing the backordering concept, how we can update our integer programming model and also the dynamic programming model. When we introduce backordering, we are going to show that. And at that point, I am going to explain that the construction of this recursive equation. And that's it, basically. That is the summary of what we have done in the last week. And we have solved the same problem using the dynamic programming approach, or namely the Wagner-Witten algorithm. And with the Wagner-Witten algorithm, we have ended up with the same optimal result and with the same policy. Here, the production quantities or the order quantities are calculated the same as the ones we have found using the solution of the integer programming model. So we are just going to introduce the backordering to this model now. First into the integer programming model, then the dynamic programming model. We are going to see these in the next video.